Okay, so although he couldn't be here, Elliot was kind enough to write an introduction, which I also added a bit to. It's a pleasure to introduce Sean Ressler on behalf of the advisor, Elliot Potter, who didn't even care enough to be here in person. It's not that Elliot was trying to avoid this, per se. It's just that the prospect of becoming chair soon was looming closer and closer.
Yes, I am interim chair.
Seeing what a good job Alex was doing, he figured there was really no hurry to return to Berkeley. If you need anything from Elliot, you can send your request to Princeton by snail mail, together with a bottle of wine. Currently, he's working on localizing the electromagnetic counterpart to today's neutron star merger with a pocket calculator. As Sean will describe in his talk, he has made significant theoretical contributions to understanding black hole accretion. Sean's work puts simpler models developed to interpret Event Horizon Telescope observations of Sagittarius A star and M87 on much firmer theoretical ground. And his ongoing work on fueling the black hole in the galactic center by stellar winds has the potential to provide a first principles model of this important system, with essentially no free parameters. We look forward to hearing all about his outstanding science over the next 35 minutes. Plus, a 10-minute bonus that Elliot is honestly a little nervous about, and he should not be held accountable for. Besides his scientific contributions, which speak for themselves, Sean has done a lot to enrich the social and intellectual climate of our department. For the last 3 years, as long as Kareem has been here, Sean has touched all the members of Elliot's group every year on Valentine's Day, when he has delivered personalized research-themed Valentine's Day cards, complete with chocolates and poems, to every single person who attends group meetings. We're talking more than 20 personalized cards every year. Kareem can honestly say, and this is just a statement of fact, not a value judgment, that the poems he's gotten from Sean have been better and more romantic than anything he's ever gotten from his partner on Valentine's Day. In fact, when he told his said partner that Sean was graduating, she said, "Good riddance, I think he's a bad influence on you." To give you a taste of what you've been missing out if you haven't been in the same group with Sean, I'm going to read a couple of the Valentine's. Climate advisors, please cover your ears. M sigma relation got you down? Try the you-me relation. Jupiters aren't the only thing that's getting hot after interacting with your atmosphere. You can cut off your initial mass function all you want, but to me, your romance function is always a power law to infinity. And my absolute favorite, this is a poem which Sean, in all seriousness, sent by snail mail to 5 members of the selection committee for a fellowship that he did not receive. Unfortunately, I will not be able to offer you a Valentine in this highly competitive year. Sean also enriches the intellectual discourse in our department. If you have an office on the 4th floor, you already know this, because you can hear him talking all the way from the physics department. Kareem has shared an office with Sean for the last 2 years. In that time, he's learned a little bit about what Sean works on. He's also learned a lot about what kind of cereal Sean likes, the details of where he plans to eat when he travels somewhere, and his opinion on various Power Rangers. It's a good thing that Sean is productive enough that he can get away with only coming to work for an hour a day, and then that he spends 75% of that hour writing the fact emails. Otherwise, Kareem would never get anything done. Once, earlier this year, Kareem was in his office concentrating as hard as he could on a really difficult problem. It had been occupying him for weeks, and he felt like he was close to getting that last bit of understanding, but he couldn't quite wrap his head around it. He was thus absorbed in deep thought when Sean arrived in the office and immediately launched into a 30-minute-long, one-sided conversation about his newly acquired Super Smash Bros. Video game. Everyone in the office tried their best to politely tune him out, but it was really impossible. Finally, after about half an hour, Sean stopped and asked, completely seriously, "Have I ever told you guys how much you distract me from my work?" The last bit of this introduction is written by Elliot only and not edited by me. Now that Kareem has probably made fun of Sean, we should say something nice about him to close this off. I know that last year, Elliot said that Drummond was his favorite student, but that's obviously not true. It's Kareem. Sorry, Sean. Just didn't make the cut. To cushion the blow, Elliot has written a poem, call it a Valentine, if you will, an ode to Sean. My Casey Sean, you inspire me to write. How I love the way you walk and stroll, always dreaming about the giant black hole. I hope that you will find yourself at home in Santa Barbara, where the physicists roam. Don't worry, folks, I don't think there's much danger in Elliot quitting his day job to become a poet. Next year, Sean will move to UC Santa Barbara, where he will continue refining his predictions of the Event Horizon Telescope's observations of Sagittarius A star. We'll be sad to see him go, but we expect to look forward to seeing great things from him in coming years. Thank you.
Can you hear me with this? Is that good? Good? Okay.
So being filmed, Sean.
So
That's enough, right?
I would say that would be very hard to top, but I think I might be able to top that. If you're willing to stay around, we've kind of gone over, and I'm probably going to go over, but if you stay around for less than minutes, I promise you will not be disappointed. And if tomorrow you decide to leave tomorrow, and you walk around the office, oh, did you hear what Sean did? And you'd be like, no, I left. And then you'd be like, oh, man. So, okay.
I'm not pickpocketing.
Okay.
I'm not doing anything lewd.
This is coming at sort of an opportune time because everybody's now heard about the NHC telescope through over and over again. Everybody's familiar with it. And so my research has been focused on different ways in which we can improve the modeling of the supermassive black hole in the center of our galaxy, Sagittarius A star. So it's a 4 million solar mass black hole. And we're modeling not just these images that you see, but also the full spectrum of the emission. And so the black hole system is really, you're not imaging, the light doesn't come from the black hole, obviously, because it's black. But it comes from the gas around it, so you give the black hole some gas, and then you end up with these event horizon images. And so I was this is a very inefficient process for the galactic center. If you give the black hole a lot of mass, there's not only a little bit of light comes out. So that you can define efficiency, and it's much less. In Sagittarius A star, it's much less than maximum efficiency, just given that all the thermal energy was emitted in light.
How good are you at talking loudly? Because the microphone is
Yeah.
weird and stuff right now.
It's not
I
working.
think I'm pretty good.
Short.
Okay.
Did you find some little knob down there?
No, there's not.
What's weird is the light is red, which is usually a bad sign. Right?
Okay.
You're probably going to have to yell.
Can you all hear me?
Yeah.
Okay, so it's much less than the maximum efficiency given by if all the thermal energy was radiated away in light. And so I was thinking about the galactic center and why I've been focused on it so much. Because as a theorist, usually you don't really get focused on particular objects. You do general models for several classes of systems, but I've always stuck around the galactic center. And I think it's because I was thinking, and I said to myself, Sagittarius A star, we're not that different, you and I. Because also, so if you give me some cheese, out comes research papers. But this is also, so if you remember, it's a very inefficient process. For galactic center. It's also a very inefficient process. A little bit of paper comes out. It's much less than 3 images. But okay, so now, just to back up, I want to give you all a broad picture of the galactic center. And I usually just have an introduction slide that maybe my little sister drew of a cartoon, or just say, oh, we have a bunch of observations over a bunch of times and a bunch of scales, but I'm just going to show a series of pictures of observational data, starting at the largest scale going down to the smallest scale. So you start off in the gamma rays, so you see these very large plumes coming out of the center of the galaxy, about 15,000 parsecs wide. And it's not really clear what these are, because for one thing, right now, Sagittarius A star is not only inefficient, but it's very low in luminosity, so it's not very active. And it could never produce, it has nowhere near enough energy to produce something like this. So one of the explanations for these features is that there was some time, maybe in 6 to 9 million years ago, it was a very active accretor. There's a lot of stuff going on, and it was very violent. There's also other explanations. That's just interesting to think about. And by the way, I'm not going to go into great detail about all these things. I just want you to have a picture in your head of what's going on. And the structure is also seen in the X-rays at a slightly smaller scale, about 500 parsecs. So this is a recent paper where they dubbed them the X-ray chimneys that sort of connect the black hole on smaller scales to the Fermi bubbles. Again, there's speculation of if that is provided by the black hole or not. Zooming even further in, this is now about 7 parsecs wide. You see these things called mini spirals, so just ionized gas, radio emission. It's not clear if these are bound streaming in or just unbound orbits coming out. And this is surrounded by circumnuclear molecular gas. And the center of this is the black hole. So you zoom in a little bit more now on basically the parsec scale. This is X-rays. This is from Chandra. So this gas now is provided by those Wolf-Rayet stars, which have been referenced in the introductions. So there's about 30 of these Wolf-Rayet stars. They're very strong wind emitters. They emit a lot of mass, and they're very fast. So they end up interacting with each other, shock heating, and they provide all this emission. And there's also some point sources here that end up, like, there's a pulsar wind nebula there. But so from this, you can estimate the temperature and the density of the gas. And so then you say, what happens if all of this spherically accretes inwards? And that's the Bondi estimate. And that's something like 10 to the minus 6 solar masses per year, which is, one, much less than the Eddington, but also much more than what actually reaches the black hole. What actually reaches the black hole is something like 10 to the minus 8. And so it's possible that a lot of this is outflow, or some of it comes in and then ends up coming back out. And part of studying how that happens is part of my research. So in infrared, Jessica will be able to tell you a lot more about this, but this is, so you see a lot of these point source stars. There's thousands of them within a parsec. And these are a combination of what are called S stars, they're Wolf-Rayet stars, and there's a whole bunch of other massive stars. But the S stars are those things you see. You see animations of them going around the black hole, turning around when they get close. So you can use the orbits of them to constrain the mass of the black hole very well. It's about 4 million solar masses, 4.3 or something like that. And because you can see the orbits moving as you observe year to year. But then, so the Wolf-Rayet stars, on the other hand, generally they're moving too slow to actually see the orbits. You get their proper motions. But they are what dominates the accretion budget. So we think that is the major source of mass that accretes to the center, where most of the emission is provided by, because a single Wolf-Rayet star is about 3 orders of magnitude higher in mass loss rate than, say, the next star. And then now going way further in, so this is close to the horizon. So at the beginning of last year, Reinhard presented these results from gravity. I won't go into great detail, but basically the Sagittarius A star in the infrared is not a continuous source of emission. It's continually flaring on and off. So what they saw was that something flared on, and then it orbited around the black hole, and then flared off. And so this tells you something potentially about the orientation of the disk and the magnetic field. So that's exciting. So that's something that people are still working on modeling now. Then at 230 gigahertz, of course, we've all seen this image. M87, it's not Sagittarius A star, but it's going to look very similar, if not a little bit more blurry, just because there's not a lot you can do with the gas around it. It's mostly a GR effect, this shadow that you see. And just to throw numbers at you, so the black hole is 4 million solar masses, 8 kiloparsecs away, so that just means it's on the microarcsecond resolution in the sky, which is basically the same as M87, which is why they're both the two targets. And you've seen this way too many times now, and you're getting really bored of it. So I want to be, my goal is to be hired by the PR department of EHT. I think they need to appeal to a younger generation, like the Snapchat generation. So this is what I have first. Maybe I can get a job. Right, okay, so I want to model the emission from the black hole, or from the disk around the black hole. It's all coming from small scale. So what do you need to model this? So first order, you need, of course, the GR effects, the per metric, which is the space-time for rotating black hole. Then you need ideal MET, you need some model for the fluid around it, so ideal MET, you throw that at it. And so this is just, you put ideal MET onto a metric and solve it. And this gives you some equations. It looks fancy because it's all in GR notation, but it's just conservation of mass, conservation of energy, conservation of momentum, and then Maxwell's equations in very compact form. Those are the equations you solve. So then you have to start with some initial conditions. And to do something reasonable, you put in, so this is a torus. Imagine this coming out of the page like this. And this is a torus in hydrodynamic equilibrium. If there were no magnetic fields, it would just stay rotating like this forever. But then you seed it with a magnetic field of varying geometries and strengths, and this is arbitrarily chosen. Then what's also arbitrarily chosen is how bound this torus is. And then what you do, you also don't know the mass of the torus. because these simulations are scale-free. They don't depend on mass. They don't have radiation. So you scale the mass of the torus until you can move basically the spectrum up and down. You can't change the shape of the spectrum, but you can move it up and down. So you change the mass until it sort of aligns with the observations at whatever frequency you're interested in. And then you just ignore everything that's happened at large radii. So this is like the simulation will expand at most, will go at most to 1,000 gravitational radii or event horizon radii. And so what happens? So now so this is actually on the board in Eugene's fluid class yesterday as we walked in afterwards. So people in the fluid class will be very familiar with this. So I'm going to talk about the magnetorotational instability. I just want to make sure everybody knows what I'm talking about because it's very important for what comes. So in the absence of any friction, you have an accretion disk, it will never accrete because the stuff, it will just conserve its angular momentum, go round and round. So you need some friction. But the problem is that astrophysical molecular viscosity are weak, and it would take forever for them anything to actually accrete. So you need something else, and one of the best candidates for this is magnetic fields. So you need strong magnetic fields in order for the magnetic field to be able to push against the fluid and cause torque. So there are two things that magnetic field does. There's magnetic pressure, which the field resists being pushed together, so it's just like fluid pressure. But then there's also magnetic tension, and that's the one that's important here. It resists being stretched apart and the field lines being straightened. So if you imagine some disk rotating around and you have two fluid elements, and say they're connected by a field line, then the one that's closer to the black hole will be going a little faster than the one at larger radii, and this will pull the guy at large radii, and the guy at small radii will get pulled back. So the one that's pulled back will then lose a little bit of angular momentum and fall in, and the one on the outside will get pushed a little bit up and gain angular momentum and go out. And when ends up happening, this is an unstable process. The one on the inside falls all the way down to the black hole, and the outside goes all the way out. So this is what allows the disk to accrete. And you can see this just by running a basic GRMHD simulation. This is not my simulation, it's taken from Chris Wright at Santa Barbara. And you'll just see it's just going to start. The right is the magnetic pressure divided by the gas pressure as well as the field lines, and the right is the mass density. So what happens is at the beginning, the field is weak, but it's unstably growing exponentially until it becomes dynamically important, and then the spore starts accreting and stuff starts falling in. So what you would like to do is then take this and see what it looks like in the spectrum and images. So there's an issue. Well, first of all, there's just an issue in general with these simulations, is that Sagittarius A star is actually a collisionless system, and what do I mean by that? So there's a time for the particles, the electrons and ions to interact with each other, both the electrons and electrons to interact with each other, and ions to interact with each other, and that's a very long time scale compared to the accretion time scale, as well as the Larmor time scale, which is the time scale for particles to rotate around in a field line. So this is a huge problem because we're using ideal MHD models which assume very strong collisionality. So we're in the exact opposite limit as what we should be. So your first inclination would be to take all these GRMHD simulations, throw them in the trash. And I'm really sorry to this guy because this had a good picture online. But so I would say not so fast because so it's actually incredible if you say you're really staunch kinetic physics guys say, oh no, this is totally wrong. These ideal MHD simulations are crap. I'm going to do these fancy simulations with particle and cells where it's completely collisionless, or something a little bit closer to ideal MHD with Broghinsky equations or extended GRMHD. And what ends up happening is that the MRI dynamics look a lot like the ideal MHD dynamics. And that's very counterintuitive, but it's because there's these things called micro instabilities that cause the field to get very tangled at small scales. So when the particles are interacting, the field acts as collisions. So there's an effective collisionality with this. So in actuality, the dynamics provided by ideal MHD may not be that bad. What is a problem is the thermodynamics, because the electrons and protons are still not communicating with each other, they're only communicating with the field. So there's no reason to expect the electrons and protons to be in thermal equilibrium. So what actually is pretty good, you need some GRMHD plus a 2-temperature prescription, and that's not bad. Okay, next slide. Okay, so how did people approach this in actual modeling? So in 2016, around there, what people did is you take a GRMHD simulation, you run it, say, okay, I have my simulation now, and what are the electrons doing? Well, I don't know exactly, I'm just going to paint them on. Like, this is not my word, they actually use the word. You paint on the electrons. You say, I want my hot electrons here, cold electrons here. So an example is, I really don't know how to say this, I'll just say Monica, 2016. I don't know, her first name is Monica, I just don't know. There's an accent. She puts the hot electrons in the jet and the cold electrons in the disk, the accretion flow. And this is motivated physically in some way. And this produces this nice little structure where at low frequencies, below the EHT frequency, the jet lights up. But then as you go closer to the EHT frequency, the disk starts lighting up. And so this structure is kind of required to match the spectrum, at least in the radio and millimeter. And some people call this a disk-jet symbiosis. And just keep that in mind for what comes next. So, but the motivation of what I first started working on was to get rid of this hand. Like, you don't want to literally be painting on electrons in your simulation. You like to dynamically evolve them. So what do? So what you do instead, you do a GMHC simulation, but at every time step you can say how much heating is there, how much dissipation versus say adiabatic compression heating the electrons and protons. So you can calculate this at every time step, and you just need some way to distribute that between electrons and protons. So we do this with some function. You say, okay, this is how much heat I have. I need to give some to electrons. And that depends on the magnetic field, the temperatures, it depends on anything you want. And so for that, you just turn to your kinetic physics friends who are doing particle and cell simulations, and they can tell you, okay, here's a reasonable function that will heat the electrons appropriately for these conditions. And one particular example we use is from Greg Powell's, that was used for the social image. It's somewhat, people are arguing about what is the appropriate function still, but that's the first thing we decided to use. And what it does is at high beta, that is low, the magnetic field is strong, or is weak at high beta, so that's in the disk essentially. The protons get most of the heat, electrons don't get much heat at all. Then at low beta, high magnetization, the electrons get a lot of heat while the protons don't get much. And this structure ends up producing this function. So this is now the electron temperature in another GMHC simulation one that I actually ran. You end up seeing, of course, that the corona is where the beta is low, high magnetization. You have hot electrons, and then in the midplane you have cold electrons. And if you remember, this is essentially the disk-jet symbiosis picture that people were doing before. So it's sort of like a more physical motivation for it, that it actually arises when you do a reasonable prescription for heating. And so this low frequency on the right, we're supposed to be, low frequency on the right is like 30 gigahertz, middle is EHT, right is infrared. And so you see the jet arises and going down is just different inclination angles. So the jet arises at low frequencies, high frequencies, the disk starts showing up, and you get a pretty reasonable spectrum. There's still some problems, but it does a pretty good job. But basically the point of my work was to say, there they are. With true temperature GMHC, you can start connecting plasma microphysics to actual observations and model features, which is sort of the first time we do this. And so our code was called HARM, and so we just added an E to it. I had more creative names, but Elliot shot them all down. That's GMHC plus these electrodynamics. We also had electron conduction I didn't talk about, but it turns out it's not important, so that's why. And so then we had a collaborator who had a code called LIGHT. Same guy names his codes. That's why they're all like, that was a radiation code. So GMHC plus dynamical radiation plus all the Coulomb coupling. So that is appropriate for M87, where the accretion rate is higher and radiation is more important. So that did some stuff. Then we also had a competitor take this model and put it into their code, which is also a radiation code, and had basically the same stuff, but they added non-thermal electrons and Powerball electrons. It's a very impressive code, actually. And so this was, Andrew Chale is now leading this. It was Andrew Oleksadowski before, but I realized after this, so the field is kind of saturated. There's other people working on similar things as I am, and it's clear that Andrew Chale is way more productive than I am in just developing citations. So I better get out of this while I can. So that's what I did. So thinking about now, what are some other problems with GMHC simulations that are doing, and how can we fix them? So the other problem is these initial conditions. I sort of tried to make the point that they're arbitrary a lot of times. Magnetic field, you just throw in whatever magnetic field you want, and you throw in a torus. There's no reason to expect there to be a torus there. So how can we either motivate these or figure out a better set of initial conditions? So that's where and also the fundamental assumption here is that the accretion physics is directly tied to MRI physics. If there's no MRI here, there's no accretion. And so all the MRI physics directly determines everything, a lot of the properties of the simulation. So how can we sort of test this? So this is where the Wolf-Rayet stars come in. I'm going to put them into my simulation, go at much larger scales now, and sort of track them as far as I go and see how that feeds the gas at small radii. So I put these Wolf-Rayet stars in as sources of mass, momentum, and magnetic fields. They go on orbits that are fixed Keplerian, and all these things are sort of set by observation. The wind speeds, the m dots, the orbits. The orbits are a little less are constrained, but they're not as well known as the wind speeds and the m dots. But you can do pretty well with that. Then in terms of magnetic fields, we don't know much, but we know that they should be all wrapping around the phi direction, not radial, just because you're at such large radii that the radial field goes to 1 over r squared, while the phi field goes to 1 over r. So it's mostly in the phi wrapping around. So I just say, okay, there's a fixed fraction of the wind. So I say this beta wind parameter is the ram pressure divided by the magnetic pressure in wind. And that's just the same for all the stars, just so we have something, one parameter to fiddle with. And then for each of the directions of the magnetic field, because in the phi direction you have to define some spin axis, and I just make that random for every star. Also, I start at the parsec scale, where this includes almost all of the Wolf-Rayet stars, and I can go down basically to almost 4 orders of magnitude, or more than 4 orders of magnitude, to almost 150 horizon radii, which is pretty good. It's not all the way to the event horizon, but that's 4 orders of dynamic range, which is nothing to sneeze at. Just to give you a picture of what this looks like, so the right is going to be a snapshot of the density as well as field lines. You see the field lines wrapping around. And the left is going to be a 3D visualization that's nowhere near as good as any of the 3D visualizations you've seen before, because I'm not willing to spend that much time on it. Don't show this to Drummond. But you see the stars. You see there's half of the stars are located in are inside a clockwise disk. So you see a lot of them going like this. And then also the simulation goes to much smaller radii. This is just to make something that looks cool. Most are interested at smaller scale. So why should you trust these simulations? Why do you trust that I'm doing something reasonable? So there's a lot of observational probes that you can test these simulations with, and surprisingly we can reproduce most of them. So first of all, the X-ray luminosity, total X-ray luminosity at large distances is, we can get that almost exactly right at large scales, just based on the m dots and wind speeds that we get from observations. This is just saying we're capturing all the hot gas at large radii, because otherwise we would overproduce X-ray luminosity. Then you can extrapolate your accretion rate all the way down to the horizon, and it turns out you're getting a reasonable accretion rate. Something very in line with all the polarization measurements and theoretical models. That also gives us confidence that we're including all the relevant mass. Then you can get the rotation measure of Sagittarius A stars to measure the field at small radii. So that's saying that the field is reasonable at small radii, as well as the rotation measure is dominated by scales about a 300 horizon radii, and that gives you essentially the time variability of rotation measure. That's also consistent. Then you can also match the rotation measure of pulsar as well as the time variability for in these simulations, and that's the pulsar in the galactic, there's a magnitude in the galactic center about 0.1 parsec, so that's a large scale field, and so you can also get reasonable field strength there. So that's just to say that these simulations, they match, they're consistent with observation basically every way that we can test. So it's reasonable to start analyzing the dynamics and thinking that it's reasonable. So what happens, so first of all, just focus on hydrodynamic simulations. Hydrodynamic simulations, what do you get? So there are no magnetic fields. These are flow streamlines, and it's phi average. Red is outflow, or red is inflow, blue is outflow. So what ends up happening is that you have a bunch of low angular gas floating around, because these stars, there's a lot of things going on. And this just ends up sort of spherically accreting, but then you also have a population of higher momentum gas that can't accrete all the way. It can only go to its circularization radius, basically, because of the concentration of angular momentum. So it will come in, and then it'll just go right back out, and this will happen, it'll preferentially go towards the midplanes, because the closer you get to the pole, the stronger the forces that pushes you out. And then on the right is just a sort of snapshot of the density on a very distinct colored car. There's not much contrast between the midplane and the poles. And then also you can extrapolate the accretion rate down to small radii, because the hole in my center of my simulation is not the black hole, it's too large. So you can say, how do the physics that the results that I'm getting depend on the size of the inner boundary? And so we find that the accretion rate depends on the square root of the radius of the inner boundary. So you can go all the way down, you can then extrapolate, assuming that holds all the way to the horizon. You get something like 4 times 10 to the minus 8 solar masses per year if you go all the way to the horizon. And that's sort of remarkably reasonable in terms of all polarization measurements, and other estimates. Okay, but then you want to turn on magnetic fields, because magnetic fields can transport a lot of angular momentum and cause, can potentially just make this picture completely invalid. So you turn on MHD, and the flow structure actually completely reverses. So now stuff is accreting in the midplane, just as you saw on the torus before, and it's getting ejected in the pole. And the field lines are bottom right. Yeah, okay. So yeah, so there's a magnetically driven outflow that's beta of 1, so the plasma, the fluid pressure is basically the same as the magnetic pressure there. So it's pretty highly magnetized. Even in the disk, or the midplane itself is beta 3, so the magnetic pressure is a third of the thermal pressure. So it seems like you would say, okay, that looks just like MRI is built up, and now it's just like a torus simulation, so what you're doing is, so what you're showing is that torus simulations are fine with MRI. And you might think that, but hold on. Then, now this is, now if we look at a aerial view, bird's eye view of the accretion flow, so now we're looking of it as it rotates around. So on the left is going to be hydro. So you see, there's two stars that sort of dominate the accretion here. And what you see is there's these things that stream, the high molecular gas sort of streams in, and then it kind of just streams right back out and has a spray that goes back out to large radius. There's no disk that forms really. There's radial velocities are high everywhere. And in MHD, you see the streams in, but then there's not as much streaming out. It's sort of just spiraling inwards. And this almost makes it look like that angular momentum is just transporting a bunch of angular momentum outwards. All this stuff that was spewing out before in hydro is now just all falling in. So you would expect the accretion rate to be much higher, or at least changed by a significant amount. Surprisingly, this is not the case. So this is that solid line is MHD, dashed line is hydro. And left is the accretion rate as a function of time through the inner boundary. Right is mass density, thermal, the radial velocity, and the accretion rate as a function of radius. And even as a function of time, everything is almost very similar. It's very, very similar, and you don't see much difference between MHD and hydro. Even though on one hand, you have these completely different flow structure differences, the movies look different, and you have strongly magnetized plasma where beta is about 2. And on the other hand, the accretion rate is going to change all everywhere. So what's going on? And here's the picture that we have come up with. So what's happening, both in hydro and MHD have this low angular gas sitting around. And it can just accrete spherically, always. But then you also have high angular gas. In the hydro case, there's a centrifugal force pushing that gas inwards, just because you get closer to the pole, you're spinning more rapidly. And so what happens is the high angular gas comes in, and then preferentially scatters toward the midplane, so you have the centrifugal force pushing it that way. In MHD, you still have the centrifugal force, but you also now have a Lorentz force that sort of tends to preferentially push it back out toward the poles. And it just turns out that this Lorentz force is stronger than the centrifugal force, so it pushes in the high angular gas that's coming in, it pushes it out preferentially towards the poles. And so in the end, it looks a lot different when you look at movies and you make time averages, but it's essentially the same gas is accreting, just as low angular momentum stuff. And the hydro, the fields just end up pushing around the high angular gas a little bit, and that's all that's happening. So what I propose that should be done, probably by myself, is that you then start looking at GeoMHD models that aren't based on MRI accretion. And it's not exactly obvious how to do that, because the reason they do is these simulations like this is easy to set up. But I can take my simulations and sort of feed them into GeoMHD simulations with some boundary conditions or something. But we haven't thought completely through it. But that's what I propose to do. And that's actually the last slide I have. So I never like reading my conclusions, so I'll just leave them up, and then I'll take questions, and then I'll have something for you.
Okay, very good. Questions for Sean? Yes, Andrea.
So 2 questions. When we turn on MHD, do you repeat the same size study?
Yes, it's still the same.
And do you fix the size of your smallest grid cell in physical units, or was the ratio of grid cells to that radius fixed? Does that make sense?
The ratio of grid cells to that radius is fixed, I believe.
Do you know what that number is?
Yeah, so the inner boundary is something like 2 cells. always.
Across the radius or the diameter?
Radius.
Sean, your previous slide, can you
Yes.
go back one slide? Well, forward then. Yeah. In this diagram here, what breaks the symmetry in the plane? Why do you have the two things going both up? You know, in the
That's just,
horizontal
I
plane.
know how else to, like, I would draw another one, but then it's just gonna be lines. But there's no symmetry breaking for the, yeah. Just because I could have drawn just another. You mean like why is like it going like this
Yeah,
and not like
exactly.
this? Yeah, just
That's right.
because it's like it depends on where the gas is fed in. So if it's fed in from this direction, it'll end up going out that way, but it's fed in this direction, it'll just grow up here. I just didn't want to draw another arrow on top of the arrow.
But it's spherical, it's spherically symmetric flow at this point, right?
No.
Wasn't this low angular?
The red stuff is spherical, but that's the higher limit stuff.
Okay,
Yeah,
all right, good.
yeah.
Yes, Chris?
Yeah, Sean, I was curious what you did about the intermounting conditions of the magnetic field.
Right, so what we did, so for the hydro, we just took away, set it to the floor in density and pressure, and zero velocity. For the magnetic field, we actually just let it freely evolve, so that flux is able to build up. And we thought that was the most physical thing to do. Other than that, you just get a very highly magnetized intermounting, but that doesn't really matter because you're not evolving it. There's potential.
Sorry, so you just let the field build up, so gas is going in, but eventually the field doesn't build.
It does go in, actually, yeah.
It keeps on going in?
Yeah, yeah,
So the field suddenly builds up?
Yes. Well, it would if the field direction that was coming in didn't change direction. So it ends up that over time the field was coming in a different direction, so it sort of regulates the total amount of flux within the boundary, and it sort of stays constant as you go to small. Because otherwise, yeah, you would be worried that it's going to start to build up so much that it's going to start arresting the incoming flow.
Eugene?
Could you just distinguish again or reconcile the 10 to the minus 6 and 10 to the minus 8?
So yes. So what happens? I don't have a plot of the accretion rate as a function of radius, but it's just the accretion rate. It starts off as something like 10 to the minus 6, and then as you go in, it's decreasing like a square root of r or something, m dot e. So that's just that's saying something about the distribution of angular momentum at large radii, because stuff at large enough radii, it doesn't care how much angular momentum you have because it's insignificant if you're, and so it'll come in until it reaches a point where the angular momentum is significant and it comes out. And so at progressively smaller and smaller radii, smaller and smaller angular momentum gas will turn around, and that gives you a distribution of m dot as a function of radius. And so it ends up. So by the time you get to the horizon, a lot of the stuff has just turned back around.
Turns back around as ejected and does not build up.
No, not at all. Yeah.
Jessica?
Is that the observational consequences or some tests that we can do?
I haven't thought of it too much in terms of like not having these MRI simulations. In terms of like EHT, it'll look the same. Because everything looks the same. But spectra. So one of the things that would be nice is because I have a mass unit here, so I have a physical. All my units are physical. So when I put it into a geometry simulation, I won't have the freedom to just say, oh, I can scale my mass up. And that'll be very nice to have a simulation where you just don't have much free parameters, you just see what happens observationally, and then you don't have to explore parameter space because there's no parameter space. So it's specific features that, one thing I'd be interested in seeing would be because a lot of the times the low frequency radio emissions explained as like the jet emission, and those are usually very magnetized jets with a lot of very little mass there. But ours are, I don't have the black hole that could potentially cause a very strong jet, but the poles are very mass loaded. And I'm not exactly sure, I haven't thought about the distribution of gas with R and how that would affect the slope of the radio, because that's important, but that's definitely something we
Chris again?
So I have a question about your description and answer to Eugene's question. The answer you gave seems to suggest that you could understand it, that the particles were collisionless. So if I have high momentum gas, then it never gets to the low momentum gas.
Yes.
It goes right through the high momentum gas, and it can't get close. But as you emphasized at the beginning, it's very collisional. Then you also emphasize the magnetic field ties it together. So how is it that this still happens?
So the key is that, like, if you think about it in like a phi average sense, you're right, you run into a problem. The key is that stuff is able to come in and go back out along different phis. So it doesn't have to intersect with its own streamline, essentially. Like, it's a lot of streamlines coming in, and then they just come out a different direction, so they avoid intersecting. That's what I picture is going on. because there's a paper in 2003 with Daniel Proga and Rich Begelman where they did something sort of like they did like a simple problem that's like has the same idea of this like you're feeding gas at large radii, and they found that it circularized very easily, but they were in 2D. So everything has to, it comes in, it comes back out on in the same direction, it has to intersect. So I think that's the key difference.
So you've got all these massive Wolf-Rayet A stars and stuff sitting around there. Every once in a while, one of them will become a supernova. So does it temporarily blow out all the gas, thus decreasing the accretion rate of the galactic center part of it?
I remember doing this estimate with somebody, and yeah, it was like so much energy that yeah, it would just blow everything away.
But temporarily, because all the
yeah.
other Wolf-Rayet A stars are going to be still sitting around
Right.
projecting winds.
Yeah, so I think like we started simulation with nothing like 1,000 years ago, so I think it would be a very temporary, depending on.
And then you don't have any inside scoop on what the EHT will have for the galactic center.
Yeah, I don't know that we tried to test them. They actually haven't analyzed the data yet. They focus all their energy on M87 because they're like, oh, Zedge near 6 stars hard.
Well, we've got a special 10-minute presentation by Sean coming up as an encore, but let's thank him for his excellent summary.
Well, I have a backup.
You want to try turning it on again? Sometimes batteries sort of charge themselves a little bit.
Alex, the antenna was tucked caught in the,
Oh, the antenna.
you see that?
Yeah. It's caught in the, oh, no, this might be too technical for me. All right. So there's the antenna out, but I'm not sure that's, I guess it's, yeah, pretend you're Mick Jagger. And,
Yeah, that's what I'm going to do.
Yeah, okay, good.
So this is good, right?
Yeah, hear me? Yeah. Okay, you can stick it in.
What?
It's better without.
It's better without? Well, I might need it actually. You'll see. So, and at the beginning of the summer, I came back from traveling and I saw, this is my poster I saw. It used to cover the whole campus, but now, here, I'll put it down for a second. But when I came back, it had sort of been pushed down off the, whatever this thing is. And I was staring at it. It even looked worse before until I fixed it. It was like really hanging. And I thought, that's a great metaphor for being a 6-year grad student. Slowly pushing you away, not aggressively, not like, oh, hey, are you graduating? But they're like, they're suggesting things. There's sort of weird whispers, like, have you read your thesis yet? Or, whoa, did John is office. You're still a student, and you're just sitting there like, I remember her still there. There's a lot of emotions that this kind of graduation brings. And people tell you not to keep your emotions bottled up and to let them out. And I was trying to think of how to express my emotions. And I thought a very good way would be through song. So what I will present to you now. It's called My Berkeley in Time. The music is by Don McLean, which is why, if you were a careful observer, you would notice he was in my collaborator list at the very beginning. The lyrics are by me, and so if I can get this mic and sound to work, and your ears don't bleed, so don't judge me on my vocal talents, judge me on the lyrics. This should be somewhat entertaining. Okay, we're gonna make sure it's coming from. Okay. Make sure it's not too loud. Oh, hold on. Okay, here we go. Long, keep Okay, I'm going to use not the microphone for the beginning, and then because it's soft. Long time ago, I can still remember how my progress used to make me smile. And I knew if I had my chance and got a few prestigious grants, then maybe I could stay here for a while. Soon I began to shiver with every paper I delivered. Got closer to my thesis prep. I just had that one last step. I can't remember if I cried when graduate I had applied. Something touched me deep inside today. I buy to my therapy in time, going heavy on the bread because it is not. When good old boys call me a doctor of science, gonna miss it till the day that I die. Miss it till the day that I die. Did you write a book on Joe? Did you invent some cosmic probe using lines of OSO? Did you forget the final goal? Can you suit the elastic flow? And can you beast without making real dough? Well, I know that you're impressed with him. That new Crosby from West. You both had the same views on the coloring stars review. So was a cock and warfare rocking buck who could simulate all kinds of stuff. But I knew that I was out of luck the day I qualified. I started singing bye-bye to my former guy. Oh, ready on the ready, cause the end is not. When good old boys call me a doctor of science, gonna miss it to the day that I die. Miss it to the day that I die. In 1 year, I'll be on my own, without Quater and without Juice Stone, but that's not how it used to be. The sixth floor rang of the research scene. In the group we gathered as a team with results that came from you and me. Oh, and while I sat there playing clown, not thinking about my cap and gown, I felt so unconcerned. No degree had I earned. When cases read my work on Star, and Stewart made a few remarks, then they said I had made the mark the day I qualified. We were singing bye-bye to these overcast skies, going heavy on the ready, cause the end it is not. When good old boys call me a doctor of science, gonna miss it to the day that I die. Miss it to the day that I die. Helter skelter in some swelter, fighting for some postdoc shelter. Deadline's near and it's coming fast. Letters from the UC brass, confirming my graduation class. Spring semester 2019 is my last. Like screens Nick tries to see you over a lazy suit, for I must now advance. Forget a job with my hands. All of my fingers try to shake the field. The referees refuse to yield. But soon enough, my fate will seal the day I qualified. I started singing bye-bye till she's bored in their pie. Oh, heavy on the ready, cause the end is not. When good old boys call me a doctor of science, gonna miss it till the day that I die. Miss it till the day that I die. Oh, and there we were all in one place, a generation lost in space, with no time left to start again. So come on, grab me nibble, grab me quick, perfect every last plotting tick, cause dire as a thesis without end. Oh, as I reached the final page, my hands were clenched in balls of pain. A research kind of hell got straight from Georgia well. As the names piled by that I decide to pass this academic ride, I saw Satan laughing with me like the day I qualified. I was singing bye-bye to my former king. I go heavy on the bread because the end it is nigh. When good old boys call me a doctor, I'm gonna miss it till the day that I die. Miss it till the day that I die. I met my longtime research muse and asked him for some happy news. But he just smiled and turned away. I went up to the admin's floor, where I'd got my office years before. But Carolyn there said to me I couldn't stay. And in the crowd my parents beamed, my mother cried and my sister screamed to see me earn this token. But I felt sad and broken. Do you see I admire most? Consider this my final toast. And tell the next grad not to boast. The day they qualify. And I was singing bye-bye to my Berkeley in time. Going heavy on the bread because the end it is not. When good old boys call me a doctor of psych, gonna miss it till the day that I die. Miss it till the day that I die.